to do optimization. So on your green sheet, do you see that it says optimization at the top? Okay. When we talk about optimization, we're talking about finding the min or max in a scenario. Now when we get to the real world problems, we're probably just looking for one of those things. So if I'm talking about like the whole thing, like number, I think it was like 65 was the computers that I was keeping in my store, and what the inventory I should have, I might be trying to optimize my profit, which would mean I want to maximize my profit by keeping the correct number of computers in my store. We might also try to minimize things like cost. Our linear programming problems are going to be pretty basic. They're only going to have two variables. If you were working a real linear programming problem, there will be lots of variables because in the real world there are lots of things that can vary. And so that's why it's called programming. To do real linear programming in the real world, you probably need a computer because there'd be so many variables we wouldn't be able to just work it out. Okay, we'd have to program it into a computer and let the computer solve it. Ours, however, lines into variables, we're going to be able to get it done. Okay. Now, do you see that checklist underneath linear programming on your notes? Okay, it's the same sort of checklist I have up here, numbered 1, 2, 3, 4, 5, 6. These are the things that we're going to do to work out a linear programming problem. And this number 1, the objective quantity, that's brand new to us. We haven't talked about an objective quantity before, so I'm going to point that out in our first example. All it is an equation that will show you what the min or max is. So when we get to the problems that are application and have some kind of scenario, a lot of times the objective function is going to be a profit equation, or it's going to be a cost equation. Okay, those types of things. You may have to set up constraints. Those are just going to be inequalities. So that would be like number 65 and 66 on your homework. You need to graph the constraints. They're all going to be lines. In linear programming, we're always going to have the or equals to, so they're always going to be solid. Okay. And then you got to find your vertex points. So you're looking for the points of intersection over that like overlap shaded area. So all three of these things are just from section 7.5. So I'm not teaching you anything new. When you set up constraints, you graph constraints, and you find the vertices. You should be able to do that. After you do all that work from 7.5, then notice number 5 goes back to that new piece that we haven't ever seen before. So after you find your vertices, you can take your vertices, all of them, and plug them one at a time into the objective function and see what you get out of the objective function. Some of them are going to be in the middle, but then there will be at least one or two that will be the max or the min. Okay? And so you'll be able to make the decision. When I plug this point in, my objective function is the highest value it ever gets. That's my maximum. And you might be able to pick out a minimum. That's how you find your max or min, the objective function. The objective function will really make more sense when we get to the third example and we apply it to a real problem. Okay? What I'm going to show you on the front side is just like run through the steps. Okay? So the first example has 4 inequalities. Those are your constraints. Do you see in the directions? Read through that real quick. Find the min and max values of z equals 3x plus 2y. Make a note to yourself. This is your objective quantity. Right now I have to provide the objective quantity and provide the constraints to you. When we get to application problems, you'll be able to write them on your own. The objective quantity, like I said, is usually going to be involving profit or cost for you. Okay, so we don't have to write the objective quantity. We don't have to set up the constraints. We're good to go for graphing. Again, notice all of these are or equals to, so they're all going to be solid lines. X is greater than or equal to 0, that's a vertical line, that is the x-axis. Y is greater than or equal to 0, that is a horizontal line, that is the x-axis. Which one of the quadrants is now shaded for both? Quadrant 1. For x is greater than 0, we would shade to the right. For y is greater than 0, we would shade above. And so we're working only in quadrant 1. Okay, that's where our shaded area is going to be. We still have 2 more constraints to graph. How would you graph those lines? Okay, Turner would solve for y equals mx plus b. Can you do that? Yeah, why don't you go ahead and solve those for y equals mx plus b right now. Or you could leave them as less than or equal to. So x plus 2y is less than or equal to 4. X minus y is less than or equal to 1. Write those in y equals mx plus b form. Isolate y. Did you get y is less than or equal to negative 1/2 x plus 2? And did you get y is greater than or equal to x minus 1? Yeah. Remember that when you divide by a negative, you have to flip the inequality sign? Okay, now when I graph those lines, I'm going to scale mine because this is so small. I'm going to scale mine by like 0.5. So every 2 units on the graph is 1. You don't have to scale yours because you can draw nicely on your paper. On the smartboard, I have a little bit of less nice writing. So I'm going to graph that first one. I'm going to go up 2 on the y-axis. And then my slope is negative 1/2. So I'm going to go down 1 and right 2. Plot a point. And I could draw a line. Think about where the shading is now. Because this is y is less than, I know that I should shade below the line. So now my shaded area is this right triangle. We have one more line to graph. That's y is greater than or equal to x minus 1. So I'm going to go to negative 1. My slope is 1. I'm going to draw that line. And I've just cut that right triangle into 2 pieces. Only one of those pieces is going to remain fully shaded for my full overlap. Since this is y is greater than, I should shade above the line. So my shaded region looks kind of like a quadrilateral, 4 sides. Questions? Places I lost people? Ask your questions now. Please don't be afraid. If you have that question, someone else probably has that question too. Yes?
But you just, in the original equation, can you just put 0 into x and y and then solve the points and then just plot those points and get the same thing?
Yes. I actually love that method, Alexis. That's one of my favorite methods to graph lines in standard form. But I asked the group, and the group said, solve for y. So I'll solve for y if that's what you want to do. Alexis's method is basically finding intercepts. So if you were to plug 0 in for x, then your y-intercept was at 2. If you were to plug 0 in for y, then your x-intercept is at 4. So you would plot 2, 4, and draw a line. It's the same line, right? Okay. In this one, your x-intercept is at 1. Your y-intercept is at -1. So -1 and 1, and we have the same line. Absolutely, I love that. Okay, you should be able to, I think on this graph, how I just pick out what your 4 vertices are. Remember, you're looking for like the corners of your shaded region. Okay, so this will be 0, 0, 0, 2. What would you guys call this point here? Looking at your graph. Looks like 2, 1. And then this one is 1, 0. Now, those are 4 of all the solutions that are included in that shaded region. So there's infinitely many solutions in that shaded region, right? Okay. But we know that if there is a min or a max, it happens at one of these corners. So we just need to test these 4 points into that objective function. So I'm going to go ahead and write down my 4 vertices. 0, 0, 0, 2, 1, 0, and 2, 1. And my objective function was, is it 3x plus 2y? One at a time, I plug those points in. So here I'd have z equals 3 times 0 plus 2 times 0, that's 0. Then I'll do z equals 3 times 0 plus 2 times 2, that's 4. I'm just testing them in the objective function. What do I get out from my objective function z? Z equals 3 times 1 plus 2 times 0, that's 3. And then z equals 3 times 2 plus 2 times 1, that's 8. Are we okay with where I got my numbers? Testing your vertices in the objective function. Remember, that's not a vertex because it's not at the corner of the overlap. So the shaded region is what we might call your feasible region. It works for all the inequalities or all the constraints. And because there's no shaded area right there next to that vertex, it's not a vertex. Well, it would just be if you graphed it in slope-intercept form, it's just the next slope. It's not really necessary to the problem. Alexis used 0 for y substitution. So either way works. Okay, are we okay with these though? Down here? Which one's the lowest? 0. So we have a min of 0 at 0, 0. You can imagine that probably happens a lot. Which one's the highest? 8. So you have a max of 8 at 2, 1. And you have made your decision about mins and max. Well, in a real world, in an application problem, it might be like $8 profit or $8,000 profit if it was in thousands. But here, there's no application. So it's just the highest value in your objective function. Does anybody have any questions about that? Okay, I'm going to skip example 2 and go on to the back side. We're going to get one of the application ones. I'm going to give you a minute to skim the problem. Example 3. Skim that problem for me. Read it. Okay, first thing you should do, just like we've done in all previous application problems, define your variables. What do you want your variables to be? Hmm? Okay, and what variables do you want to use? Which letters? X and Y. Okay, so we're going to say X is, Turner says, the $250 model. Y is the $400 model, and that's really saying like the number of those models that you're keeping in your inventory, right? Okay. Now, what is the problem asking you to do at the very end? Find the number of units of each model, so that helps us define our variables. What else do we want to find? Okay, maximize profit. So that's telling you what your objective quantity should be. Do you want to minimize cost? Do you want to maximize profit? Okay, what are you trying to do? Since I'm talking about profit, I'm going to use a P equals, my profit equals. You could say Z equals here if you want, but I often use P and C. And then go back into your problem. What are all the numbers that have to do with profit? $45 and $50. So for every $250 model, I'm going to make $45, so 45x. For every $400 model I sell, I'm going to make $50, so that would be 50y. At this moment, I don't know what my profit is going to be. It just depends on how many DVD players I sell. After you write the objective quantity, then you got to read back in and do all your constraints. So what are the things that limit you? The total monthly demand and the amount of money you want to have in inventory, or the amount of DVD player that you want to have in inventory. So what's the monthly demand for DVD players? No more than 250. So I'm not going to sell more than 250 DVD players in a month. So that would say X plus Y should be less than or equal to 250. Okay, my demand, I shouldn't buy more than my demand. The other thing Alexis brought up is I don't want to have more than $70,000 in my inventory. So you're going back and you know that when you have this $250 DVD player, for every one of those, that's $250 of your inventory. So your inequality there would be 250x plus 400y should be less than or equal to 70,000. You could. I'm not going to. But you could. Are there any other constraints in this real world that we live in?
X must be greater than or equal to 0.
It wouldn't make sense for me to have less than 0 DVD players. So we're really going to concentrate in the first quadrant. Now, we want to find the vertices so that we can plug them into the objective function that we wrote and find the answer, what's our maximum profit. But first we've got to graph. Now, I'm only going to graph like the x in the, or the first quadrant, the positive x's and the positive y's, because you guys gave me the real world constraints, x has to be greater than or equal to 0, y has to be greater than or equal to 0, right? So I don't have to really worry about graphing those. Okay. Now, can I go back to Alexis's method for graphing lines? It works out so smoothly on these problems with these big numbers, which is why Bailey, I wouldn't simplify that because I'll use Alexis's method. Okay, her method is, in this equation, x plus y is less than or equal to 250, find your x-intercept and find your y-intercept. And just plot those 2 points and then draw the line that connects them. To find an x-intercept, y must be equal to 0. So if you put 0 in for y, what's x? 250. To find your y-intercept, put 0 in for x. What's your y-intercept? 250. So I decide, okay, I go to 250 on both of these. I'm going to scale by 100. I'm not going to beat myself up over drawing the most perfect graph ever. And I'm going to mark an x-intercept and a y-intercept at 250. And draw the line that connects them. On these problems with these large numbers, that's probably way easier than counting slopes. Then you don't have to have as nice of a graph. Now, where would you be shading? Below. You could do a test point for this one. Maybe test 0, 0. 0 plus 0 is less than or equal to 250. True or false? True. So you should shade in the direction of 0, 0, which would be forming that right triangle. Now, let's do that other equation, and somebody's going to have to pull out a calculator for us. We're going to do our x-intercept and our y-intercept again. For the x-intercept, I would plug 0 in for y. 250x equals 70,000. We just have to take 70,000 divided by 250. 280. So my x-intercept is at 280. For my y-intercept, plug 0 in for x. 250 times 0 is just 0, and then you have 400y equals 70,000. 70,000 divided by 400 is 175. You see what I'm doing there? Does anybody have any questions about that? I used to teach that in Algebra 2, and I would call it the cover-up method. Just cover up the x's and solve for y. Cover up the x's, or the y's, and solve for x, and you have the intercept. And do the other. Okay. So I'm going to plot those. 280 is my x-intercept. And 175 is my y-intercept. Where's my shading? Still below. Yeah, because like 0, 0 would make this true. So this area is shaded. And then I want to pick out those 4 points. Olivia. Because this part right here? Yeah. Because if I test in this line right here, if I test 0, 0, 250 times 0 plus 400 times 0 is less than 70,000. Do you agree? Okay, so that was this line right here. I have to shade below that line. Yeah, but that's not overlap. It has to be the places where the shading works for everything.
Oh.
So like, yes, this is shaded, but it's not overlapped by the other one. So I'm only looking for the section where the shading works for everything. This is greater than x, this is greater than y, this is less than the first line we graph, and less than the second line we graph. Alright, some of these are easy, right? 0, 0. This was our y-intercept, 0, 175, and our x-intercept, 250, 0. The one point we have to find is that point where the two lines cross. How could we find it? You could set them equal to each other as I have them written right now. What might you do? You could do substitution. If I had these two, I would probably do elimination. If you solved for y to graph those lines, then yeah, they're both equal to y, you could set them equal to each other and solve. But the way that we have them written, I would think about it as, I want to take x plus y equals 250, and 250x plus 400y equals 70,000. And I want to solve that system. To me, that's set up very nicely for elimination. So I would maybe multiply this first one by negative 250. So that my x's will cancel. So I'd get negative 250x minus 250y equals 62,500. Yeah, negative 62,500, thank you. And then I get 150y equals 7,500, so y equals 50. If y is equal to 50, what's x? 200. Just plug it into that top one. X plus y must equal 250. So x plus 50 equals 250. X is 200. So now I have that final vertice. So I'm all for it. Then what do you do with those vertices? Plug them in and see which one gives you the highest number. That's your maximum profit, right? I'm going to out of room. Maybe do this. Well, you know what to do. Let's see. If I plug it in, I get 0. This time I plug in 0, 175 to our objective function. What is it? I'll have to talk quietly. Sorry. You think I can hear? Great. Okay. We're plugging into 45x plus 50y. And you're just plugging in your coordinates. Did anybody get 205 or 50? 10,000? Okay. Just type it in a calculator. 11,250. And anybody got the last one? 45 times 250.
Oh, I was finding a different order than you.
Okay. Does anybody have any that they can give me?
Yeah, I like the last one.
Okay, what's the last one?
I got this big.
45 times 250?
I got 11,500. Yeah.
11,250.
200.
What about 250?
I got 2 million.
Are you plugging it into this?
Yeah. Did you multiply them?
45 times 200?
Hold on. Let's add them.
Oh, I
Yeah, I got
Thank you.
them.
Somebody give me that number.
I got 11,000.
11,500.
So 200.
Wow, that's a lot of work. Which one of those is the highest? That part's supposed to be easy once you find the vertices. The highest one is 11,500. So, the Are we a shop owner? The company should keep 200 of the 250 model and 50 of the $400 model for a profit, or a max profit of $11,500 if we did our math correctly. What's that? Now, at the end of the linear programming problem through the application, you should have some kind of statement there. And it's not just like write down an answer, like give me a spiel about it. What should I keep, okay? Get started on your homework. You'll want to come with lots of questions tomorrow. We'll do another day of linear programming and then get started on the Chapter 7 review.